means is to look at the final step, the backward substitution. That is to solve u for u, the unknown. So we have said that what we need to solve now is the u equal to c, because the c contains now our y, the intermediate solution. So then we write down what was our upper triangular matrix U. There we had overwritten the delta by the d, so it is the d1 here. The a's are unchanged. Then the delta 2 was overwritten by the d2. a2 was unchanged. And that is continuing all the way down to a nj minus 1 and to d nj minus 1. And the final element in the diagonal is the dnj. So then we have this matrix. So we have in the diagonal the d's, which contain the deltas, because we have overwritten the d by the delta. And above we have zeros, and in the lower triangular part we have zeros. So that is our matrix U. And our unknown that we want to determine has then the components U1, U2, and so on, UNJ minus 1, and UNJ. And the right-hand side, that was containing the Y, and we have overwritten then the C with the Y, so it is now the C, C1, C2, and so on, the C, NJ minus 1, and the C, NJ. So that is what the system of equations that we have to solve in this step. And this is the U, and this is the C. So to solve this system of equations, we start at the very end, because there we have just zeros. Then we have d and j that we know times the u and j that we don't know is equal to the c and j that we know. So that means we can determine the u and j directly by computing the ratio between the c and j and the d and j. So we have to do a divide here. No problem. Then we go to the next but last row to determine the u and j minus 1. And there we see we first have to compute, this is the c and j minus 1, that is on the right hand side. Then we'll have the minus u a and j minus 1 times the u and j, which we know, so we therefore get on the right hand side with a minus. Minus a n j minus 1 times the u and j that we have just determined. And then we have to divide by the diagonal element, which is the d n j minus 1. So this pattern will then continue. We'll take, say, the u n j minus 2 as an example. We will have on the right hand side the c nj minus 2 minus, we will then have the a nj minus 2, that is then multiplying the u nj minus 1. So imagine here, here, so then this will come into play. So the diagonal element will be the d nj minus 2. So we see this pattern will just continue. So then from that we can see that the backward substitution becomes following. That is the algorithm that we later will also use, again use the override trick. But first we just take it as it is. We don't need to override here actually, we can just take it as it is. The U nj is equal, that is the first one, that is equal then the C nj divided by the B nj. That is the first one, which is exceptional. That is just to start with. But the other ones have a similar pattern. They are the Uj equal to the Cj minus the Aj times the Uj minus Uj plus 1. See, here we have Nj minus 1, Nj, Nj minus 1, Nj minus 1. So it is the Uj plus 1 divided by the Dj. And remember, the D here is what we had originally as the delta, and the C that we have been using here is originally the Y. And let's see, that's it. So we have used this. And that is done what we have here for j equal to nj minus 1, and then we go up to 1. So therefore backward. We start from the end and we go backward. One could also use the override again and override the C with a U. That's possible, but we don't need to do it. Anyway, the steps that we saw, the LU decomposition, that was the formula. You have it in your notes. That is then the LU decomposition, that was the 5. So LU decomposition that was 5. And then the forward substitution, that was 7. And what we have seen here, the backward substitution. This is the 8. So all this, that is the Thomas algorithm. Or the TDMA. So what's the general advantage doing this and not doing LU decomposition, because the steps are very similar? The advantage is with the LU, with the Gaussian elimination, you usually just get the U and the upper triangular matrix and you compute the solution while you are doing it. But when you then want to do another right-hand side, you have to do the things all over again. If we do it this way, we can reuse the LU decomposition. We can just take another right-hand side, then we have only to redo the forward and the backward substitutions. And the most work is in general the LU decomposition. So when we have many right-hand sides, it makes sense to store the LU decomposition and then to reuse it. So that's the advantage of doing that. And for the algorithm that we have here, we have these steps, and if you count the number of operations, you will see that the operation count for this here is, let's see if we can make a little list of that. So we call it the floating point operations. Floating point operations. And the floating point operations are plus, minus, times, and divide. If you look at the algorithm, you will see that the LU decomposition involves 3 n operations. N is the number, in our case we have the nj. So let's use the notation. It's, well, It might be plus or minus 1, that is not interesting. Interesting is what's the factor here and what's the dependence. Depends on the number of unknowns, nj unknowns. Forward substitution, if we look back, we would find it is 2nj, and for the last one we can just count it. So this we don't need to count, that is would be just one operation. This is the interesting one. Here we have a minus, one operation. Here we have the times, second, and the divide, 3 operations. It's a little unfair because the divide is taking much more time than the plus, minus times, but we do it like that. So that means we have also here 3nj. You see again it is not exactly, because you would have in fact minus 1, we don't, because minus 2, because we have only one operation here, but 3 in general. But we don't bother about that. So in total we have then a number of operations is 8 times nj. So that means the number of the amount of work goes with the number of unknowns times 8. That's it. So then we have this Thomas algorithm, and that is built into many problems. So it's useful to know about that, and also to write a little function to do that. So little test for this algorithm is the following. So first, just to give you a view what this could be. So I have just the algorithm itself. There. See, this is the function that no, that is just the function that is testing it. So it's calling, so it's generating the sparse matrix, which is in that case a 10 by 10 matrix with 2's in diagonal and minus 1 in the off diagonals. And the right hand side is, in this case, it is an x squared, but I have also the option to take a random vector. And then the Thomas algorithm is called. And as comparison, we also have here the backslash to see the timings. So the Thomas algorithm, let's see, this is the interesting one here. So you see just the very few lines here. We give in the diagonal, the upper of the subdiagonal and the lower subdiagonal. You see here I did a little trick. I call this BB because the B I want to have indices from 2 to n. So n is here my, let's see, nj is the length of the vector. So I get that from here. So then I get the b, as in the code, from 2 to n to b, the bb that is entering. The bb is an nj minus 1 vector. So therefore the b1 is, or the bb, let's see, the b1 is 0. So by the way I did it here. And then this is the first tool is the LU decomposition. This is a forward substitution. And this is the solution at nj that we have there. And this is the rest of the, so this is the vector substitution. So you see here it's very, very little, just very compact, and that's it. And then in the end, you have the solution vector, which is called x. So let's see what we get out of this. Yeah, I plotted also the solution here. I assume then that this was an x squared on the right hand side. That is not so interesting. Interesting is the timings. The first timing is for the backslash, so which is quite fast for this, and this is for the Thomas algorithm. So we need a little overhead, we need to call, so that's the reason why this is slower. The LU divide will use Cholesky decomposition. That is a different one that we use. And the difference in the solution computed by the ML divide backslash, and the Thomas is in the order of the machine epsilon. So if we increase the number of points, so let's see, I can also take this away. Well, no, okay, let's take it as it is. We can go to, let's see, we can go to 100 and run it again. See that? Okay, you see no difference here between Thomas and the ML divide. Here now the timings get a little closer, but still it's an advantage for the ML divide, but the difference gets larger because the ML divide uses a method where the spreading of rounding error is less, so that is better controlled than in the Thomas algorithm. So this difference will increase if we take larger values. But it is still, it's slow. It depends then also on the condition number of the matrix, which is then responsible for the spreading of rounding errors. Let's see that one. You see now the timings are already reversed. Now the ML divide takes more time than the Thomas algorithm. Of course, the Cholesky in that case, or the operations that they have to do, is larger than the Thomas algorithm, which has only 8 NJ operations as we saw, but the difference is still increasing. And that will now continue, and if we have 1,000, if we have 10,000, we have to wait for the solution with the ML divide, while the Thomas is just giving us the result very, very quickly. So this is a useful algorithm, but as we see with the difference, the spreading of rounding errors is larger with the Thomas algorithm or Gaussian elimination with partial pivoting than it is with the Cholesky algorithm that they are using. So here you see a clear advantage of the Thomas in the timing, which is much less than the ML divide, but the difference is increasing. Okay, so that gives you an idea of the Thomas algorithm. Now the Thomas algorithm is just one special class of the direct methods that we can summarize under LU decomposition, which is essentially Gaussian elimination. So let us now just take up this, because it is useful to have a basic understanding of the number of unknowns that you, the number of operations that you have to do this LU decomposition, like we had here in this special case, which was only 8 NJ operations, but in the general case this is much more. So we are exploiting here the band structure. So, what is then the LU decomposition? It's sometimes also called LU factorization. And if you do the Gaussian elimination, we get essentially what we need here. We just have to collect the numbers in the process when we do it. So, and we get the following. We get a permutation matrix P, that is doing the row interchange, that is multiplying the matrix A, and what we get then is these elements that we have to do the pivoting with, that is then getting us the lower triangular matrix to 0. These elements then contain the L matrix, and the upper triangular matrix is the one that we get in the end at the end of the LU, of the Gaussian elimination. So the P is the permutation matrix doing the row change. So it contains just a permuted unity matrix. So it has ones, only ones, but at different places around. So that does the reordering of the rows such that the pivot element is the largest in the column that we consider. So below there are only entries which has an absolute value that is smaller equal than to the absolute value of the pivot. That is in order to control the rounding. And the L and the U are lower and upper triangular matrices. So the L is, say, we write this way, contains the ones in the diagonal, as we saw also for the tridiagonal system, zeros above. So that is a, as we saw before, that is a lower triangular matrix. So that is the L. That is then multiplying the upper triangular matrix, where we have something in the row, not necessarily one, usually not, and something above but zeros below. So that is the upper triangular matrix. U. So then we do an LU composition not of A, but of the pivoted matrix PA. Okay. So the solution is done in a similar way as we discussed for the tridiagonal system. So the solution of our system that we discussed in the beginning, that is done in the following step. We use, instead of this, we solve P AX equal to PB. So that means we multiply our whole linear system by the permutation matrix. That is, we do the row interchange both on A and on the right hand side. And then we use that the PA is equal to the LU. So that is the LU, then we solve LUX equal to PB. And that we do then in two steps. We call this again Y. So that means we do first we do well, we assume that we have done the LU decomposition. Now, for the solution, we do first the forward substitution. And that is then solving the system Ly equal to PB. In our case, that we discussed before, we did not have to do that. The P was the unity matrix. That is when we don't have to do pivoting. So that is easier, but this is no problem either. So then we do the forward substitution. And then, when we have done that, we do the backward substitution. Then, backward substitution. And that is then, we solve then 11, we solve the rest, that is the U, X equal to Y. So that is similar to what we discussed for the tridiagonal matrix. us now look at the floating point operations and the storage requirement for the general LU decomposition and forward-backward substitution. Floating point operations. That is what we call here the flux. Don't mix that with floating point operations per second. That is something different. That is, say, the performance of the computer. Here we just count the number of operations, floating point operations. And we look at the storage requirement. That we do in words, computer words. So then we can make a little list. Table. Where we have flux. Where we look now at two different types of matrices. We look at a full n by n matrix, and we look at a n by n band matrix. So the tridiagonal matrix is an example. We assume that we have a bandwidth which is realistic for also what we have in CFD W, which is usually much smaller than n. In our case, for the tridiagonal system, W is 1. We have only bandwidth is just 1. And we also assume that we have no pivoting, because pivoting usually can give some problems. So then we have this table, and here we have the LU decomposition, and we will also consider the forward substitution, and we will consider the backward substitution. And then we will also consider the storage words, how many we need. So it turns out, for a full matrix, that we need approximately 2/3 times n to the power 3. And this is a problem when we have large n. If we want to increase that, it gets very much larger when we then increase the n, because it goes with the power of 3. Opposed to that, we have, with a band matrix, then with W, we have n to n W squared plus nW. In the example that we had just discussed before, the W was 1, 2n plus n is 3n. That is what we said there. So that is okay for our tridiagonal matrix. If we do the forward substitution, then we have to go through the whole matrix, but it's just a lower triangular matrix. And the operation count is approximately n squared, whereas for the band matrix we have approximately 2n W operations. Again, okay, for tridiagonal matrix there we have 2n for W1. For the backward substitution we have also approximately n squared. And if we look at the band matrix, because of the divide of the central element U, we have there 3n W operations. Regarding the storage, we have n elements, n rows and n columns. We have to store n squared words. For the band matrix, we have n in the diagonal, n minus 1 in the next diagonal, and so on. So it gets less and less, but approximately we will have there 2w plus 1 times n. For the tridiagonal matrix, we have just 3 diagonals to store, the main and the 2 subdiagonals, so that is then 3. But if you would have larger, then you would correspond to that. But this gives you some indication, and it also shows you that it's much better to have band matrices. But again, I stress it is important you have no pivoting. So that is what you can expect from the operation count, and that we have to compare them with the operation count that we have with iterative methods. In CFD, it is quite common to use iterative methods in 2D and 3D. But if you have problems that are not too large, you have band matrices, you might consider to use this technique, LU decomposition, forward-backward substitution. There's also a technique which is related to the one that we discussed for the tridiagonal matrix, when you have block tridiagonal matrices. Then we can use similar techniques as before, but for the blocks. So they are also quite common in CFD. Just to tell you about another, there is one thing that is important. That is a note. The note here that you should also know when you do LU decomposition, forward-backward substitution, is the following. When we have the problem that we are discussing for exercise 10, we have a diagonal and we have 2 subdiagonals which are tight, so that they are directly adjacent to the main diagonal. But we have also diagonals which are off. Actually, in our case, the bandwidth that we discussed is Ni, if you remember. So the bandwidth is Ni here. But we have zeros in between here. So it means we have only 5 diagonals that we are working with for the A matrix. But when we do the LU decomposition, we get the following. We get 1s in the diagonal, that is no problem. We get here, close, we get a diagonal, close, subdiagonal, that is no problem. But we get now, in addition to the lower diagonal that we have here, we get more. And that is the problem. We get something in between here. And that is called fill-in. And that is giving us more work, because we have to compute all these elements. So this is all this area here. You get a bunch, actually it will be Ni minus 2. Where we had the zeros before, we will get something. And the same thing is happening also for the, so that is the L, and it is also happening for the U. Originally we had just something in the diagonal, something above, and something away. But also here we get a problem. Here we get something that is giving us here some, it's called fill-in. So we get here a bunch of also Ni minus 2 more diagonals where we have to compute and to store the elements. So that is the U here. We have still zeros here, zeros there, zeros here, and zeros there, but the red, that is called the fill-in. That is the fill-in. And that is causing us more work and more storage. More computational work. And we you need more storage. There is a technique called incomplete LU decomposition, where you stop at some point and you accept that you don't do it accurately, but only approximately the solution, and that is sometimes useful as, say, as an approximate solution. Okay. So just for your knowledge, it's interesting to know also about the method that the MATLAB is using as a preference, and that is when we have proper matrices, so it does not work by far, not for all, but for certain class of matrices that we actually have in our example, we can do the so-called Cholesky factorization. That is called after André Louis Cholesky, French officer and mathematician, who died shortly before the end of World War I. And there we need that A is symmetric, so that is what we have in our case. A is equal to A transposed, and we need that the matrix is positive definite. So, and that was giving us, when we do a multiplication of a vector X transposed times the matrix A, that gives us something positive for all vectors X that are not zero. If we have such a matrix, then there exists a unique lower triangular matrix L with positive diagonal elements such that following holds that A is equal to L times L transpose. So that means our upper triangular matrix we don't need to compute. We just have to transpose the L, so we only have to do half the work, half the storage, because we don't need to store the U, just the L. So that is the advantage. But the prerequisites are, and that is satisfied for our elliptic problems that we are now considering, but by far not for all problems that we have. So the advantages of this technique is we have no pivoting needed. And the other advantage is we have only half of the number of operations needed for the L transposed factorization, n to the power 3 divided by 3. So that is half of LU. Then we have 2/3. And the other advantage is we have only L needs to be stored. And that is also half of LU, so we don't need to store the U. So one can say much more about this direct method. So they have there is also another method called cyclic reduction. So you have heard that, so I tell it to you. But if you want to have a good reference for that, also for the coming iterative methods that we shall discuss tomorrow, I recommend the book by Jean Gollop and Charles Van Dam. And that book is called Matrix Computations. It's now in the 3rd edition, and that is of 1996. There are also other very good numerical algebra books, but this is one classics book. And regarding the software, we have MATLAB, and there we have the LU is a function, so there you get P, you get LU and P by that. And we have the ML divide, that is the A/B, so that is then all built in, so that is very nice. And we have also the Cholesky decomposition, it's also built in MATLAB. There is a package called LAPEC, linear algebra package, and LAPEC++, so that is for Fortran 90 and that is for C++. And there you have similar direct methods, so based on a U decomposition, forward backward substitution, and on Cholesky factorization. So there is a lot around that. There's also commercial software around, for example, by NAG. But I would say these have good reputations, and you know MATLAB by now quite a bit. So this is ML divide is quite good, but when we come to large number of unknowns, then it fails or it takes extremely long time. You saw already with, I think I had 10,000, it took quite a long time to get results. So there we have then an advantage of using iterative methods that we shall discuss tomorrow.